Hello, in this episode we will be looking at the curl and deriving an expression for the curl in any orthogonal basis. So when we're calculating the curl, what we're going to be doing is taking a really small integral around this loop and essentially adding up all the components. That will give us a measure of the vorticity or the swirliness of our vector function A in this little piece of area. So what we're going to do first is we'll look at these two sides, this one and this one. So so our curl is essentially going to be this loop integral divided by the area of the loop. So let's take a look at that first side there. So that component there, so we're going to have the integral of A dotted along the direction of that piece of loop. And so that's going to give us the A1th component of our vector evaluated at x1, x2, and x3. And because this is a really tiny piece of length, we're going to assume that the A vector is constant along that length, and we're going to multiply it by the length of the little piece, and that length happens to be h1 dx1, so it's multiplied by h1 delta x1 . Now we want to find the other side. Now this one, we're traversing the loop in the opposite direction of our dl component, which is so our dl component in this case, so we've got the integral of a dot dl. Our dl component is going to be minus dx1, because we're going in the opposite direction if these are our unit vectors. We've got x1, x2, and x3. So you can see that it's we're going that way, so it's the negative dx1 dotted with our a. It's an integral, so we're going to have minus a1, because we're only getting the a1 component along that, evaluated at x1, x2 plus delta x to x3. And again, because it's constant along that x1 direction, because we've got a really tiny length, it doesn't matter whether it's x1 or x1 plus delta x1. We'll make it x1 plus we'll make it just x1 in both cases, so that what we end up with is something that kind of looks like a partial derivative. So let's go ahead and add these two components together, and we also need to multiply by the length of this component, which is h1 delta x1. Now let's go ahead and add these two components together. So we've got a1, so we've got h1 delta x1, and we've got a1 evaluated at x1, x2, 3 minus a1 evaluated at x1 x2 plus delta x2 x3 like so. Let's go ahead and shift a couple of negatives around. So we're going to have negative h1 delta x1 so I've pulled this negative out the front, and we're going to have a1 evaluated at x2 plus delta x2, given that everything else sort of stays the same, minus a1 evaluated at x2. Now we can multiply and divide by delta x2, and that will give us something that looks like our partial derivative definition. And we'll let all of our deltas go to d. So delta going to d, or going to basically 0, just a really tiny infinitesimal length. And so this term here is our partial derivative. Actually, we need these h1s to be inside, because they are going to change depending on where they're evaluated. So we're going to have this formula here. It's going to simplify to minus dx1 dx2 del h1 a1 over del x2. Now we can do it for the same thing for these two sides. So we'll take that bottom side first, this one here. We'll say we're going from this point to this point. So we can assume that a distance delta x2 is really, really tiny. So we're going to have our a dot dl is going to be equal to, so we're going in the direction of x2, so this is going to be a positive component. We're going to have a2, because it's just the component pointing along that line, evaluated at x1 plus delta x2. So it doesn't matter, delta x1. So it doesn't matter whether we evaluate this at x2 plus delta x2 or just x2, because it is such a tiny length. We're going to assume that it's basically constant along that length. So we're going to have that, and we need to multiply by the length, which is going to be h2 delta x2. Yep, that's right. And then the other side is going to be the integral a dot dl. Now we're going in the opposite direction of the unit vector x2. So we're going to end up with h2 minus, because we're going in the opposite direction, delta x2 a to the tooth component of a, and we're going to evaluate that at x1, x2, x3. Now we can add these components together, multiply by delta x1 and divide by delta x1, and end up with a similar expression. So we have delta x2. I'm going to multiply by delta x1 now. We've got h2 a2 evaluated at x1 plus delta x1 minus h2 a2 at just x1, and the other components stay the same. And we multiplied by delta x1, so we're going to divide by delta x1. And this is our partial derivative. Letting out d's, letting out deltas go to d's. We're going to have dx2 dx1 del h2a2 over del x1. And then we're going to add this to the component we had before, and then divide by the area over which we took it. So that's minus dx1 dx2 del h1a1 divided by del x2. And then we're going to divide all of this by the area of our loop, and the area of our loop is going to be h1 dx1, because that is the length of one side, multiplied by h2 dx2, the length of the other side, those scale factors turning these coordinates into length values. And then so we get some nice cancellation, bang, 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 bang. And we're going to end up with 1 on h1 h2 del h2a2 on del x1 minus, so that 1 on h1 h2 is on both, del h1a1 del x2. Now this gives us a vector pointing in the E3 direction. If you recall, maybe the right-hand rule or something of that type. If you're looking at torque or angular momentum, that's usually how we define those vectors. Something that is swirling in this direction will have a vector associated that points up. Similarly, if we have a vector pointing in that direction, let me just make sure I've done the same thing. That direction will have a vector pointing down. Now we can just commute these values and get the E1, E2 vectors as well. I'll just do that quickly. So we'll have 1 on, if you see a 1, turn it into a 2, 2 turn it into a 3, and a 3 turn it into a 1. So it's 1 on H2, H3, del H3, A3 on del X2 minus del H2, A2 on del X3, E hat 1, and 1 on H3, H1, del H1, A1, del X3 minus del H3, A3, del X1, E2. And that is the curl in a arbitrary orthogonal basis set in 3 dimensions.